Good morning everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we will talk about plate buckling. Particularly, we will talk about the von Karman's equations for plate buckling to determine the critical stress for plates. So, let's look at the summary of the global buckling columns that we have done. In the previous classes, we have limited the column strength to Euler load P critical due to assumption of doubly symmetric prismatic section. So, here P critical equal to pi square EI by KL square. However, columns do not fail by flexural buckling alone. We have obtained the critical loads for columns using the energy method. Here the total potential energy of the member is given as pi equal to U plus V, where U is the strain energy of the beam and V is the potential energy. The equations are given here. Solving U plus V and minimizing that with respect to the constants, we get the cubic equation for the critical load given here. So, depending upon the shape and dimensions of the cross section, we can use the following simplifications. Here, for these cross sections, the first section is an I section which is doubly symmetric, the second section is point symmetric. Here, the shear center and the centroid coincide, so x naught equal to y naught equal to 0. So, P critical is given as minimum of pi square EIy by L square, pi square EIx by L square and 1 by R naught square into Gj plus pi square EIw by L square. The first two terms corresponds to flexural buckling. The third term corresponds to torsional buckling. Now, for monosymmetric cross sections or singly symmetric cross sections, here y naught equal to 0 for channel sections as well as in angle sections. So, the P critical is given as minimum of pi square EIy by L square or Px plus P gamma divided by 2 into 1 minus x naught square by R naught square into 1 minus root of 1 minus 4 Px into P gamma into 1 minus x naught square by R naught square divided by Px plus P gamma the whole square. Now, the first term here again belongs to flexural buckling, the second term corresponds to flexural torsional buckling. Now, let us look at the summary of global buckling of beams. Now, for laterally unsupported beams, where the displacement goes in y direction as well as in u direction as well as there is a twisting, also known as lateral torsional buckling. As you can see from the right hand side of the picture, which gives a lateral torsional buckling for an I section. The elastic critical moment is defined as M critical equal to pi square EIy divided by L sub Lt the whole square into root of Iw by Iy plus Gj into L sub Lt the whole square divided by pi square EIy. This is for doubly symmetric cross sections. A much lengthier equation is shown below with the coefficients C1, C2 and C3. This is for monosymmetric cross sections about minor axis. So, there are other failure modes for beams and columns as well. The columns, as you can see, is subjected to uniform compression, whereas the beams are subjected to a stress gradient. Structural steel sections consist of plate elements such as flanges, web and stiffeners. Under compression, the elements with high slenderness ratios, that is high width to thickness ratios or depth to thickness ratios, become unstable and buckle locally as shown in the figure. This phenomenon is known as local buckling. So, the local buckling is shown in the dotted line here. A blown up view is also shown on the right hand side, where you can see that the half sine wave buckling is also mentioned. The edges here are one which is a free edge and number 2 is the simply supported edge. Basically, it is the junction between the web and the flange. Now, when does local buckling occur and what is the critical stress for the plates? These are the questions that we need to answer. To answer these questions, we need to have a fundamental understanding of the linear plate buckling theory. Let's look at it. So, consider a plate of uniform thickness H, as you can see here, and the axes are shown here. Right hand side is x and towards the out of the plane is y, and in the true thickness direction it is z. Let's consider a small cube with the dimensions dx, dy and dz. The stresses at any point within the plate can be represented in a material point as shown in the figure here. So, the sigma x, sigma y and sigma z are the normal stresses that are acting, which is shown in the red color, as well as the shear stresses that are acting here shown in the blue color. The tau xz indicates force x in the direction of z. So, the first nomenclature indicates the force, the second nomenclature indicates the direction of the stress. Assumptions for buckling of thin plates. The shear strains gamma xz and gamma yz are negligible. The lines normal to middle surface prior to bending remain straight and normal to the middle surface during bending, which can be seen here as tau zx equal to tau xz equal to 0. Similarly, tau yz equal to tau zy is equal to 0. The normal stress sigma z and the corresponding strain epsilon z are negligible, and therefore the transverse deflection at any point xyz is equal to the transverse deflection of the corresponding point xy0 along the middle surface. So here sigma z is equal to 0. Further assumptions: the transverse deflection of the plates are small compared to the thickness of the plate. Thus, the middle surface stretching caused by bending can be neglected. That is, the membrane action resulting from flexure is negligible compared to the total flexure. The material of the plate is homogeneous, isotropic, and obeys Hooke's law. Now, substituting tau zx equal to tau xz equal to 0 and tau yz equal to tau zy equal to 0 and sigma z equal to 0, we get a small piece of plate, as you can see here. The forces that are acting in the x direction are Nx, and the forces that are acting in the y direction are Ny, and the shear stresses that are acting are shown as Nxy, and the complementary shear stresses that are acting are shown as Nyx. In plate theories, generally the unit of force used is load per unit length, which is Nx equal to sigma x into h. The forces are positive in the considered direction as shown in the figure. An element of laterally bent plate is acted upon by two sets of forces. The in-plane forces, which is Nx, Ny, Nxy and Nyx, equal to the externally applied loads, and the moment and shears that result from the transverse bending of the plate. Now, let us establish the equilibrium condition for these two sets of forces separately. So, when we have this lateral deflection W, the deformed shape is shown here on the right hand side. So, the slope here is given as dou W by dou x in the x direction, and in the y direction it is given as dou W by dou y, and the forces are shown here, which is Nxy and Nyx, and the Nx forces here on the left hand side it has a slope of dou W by dou x, and on the right hand side, due to a small increment, it has a slope of dou W by dou x plus dou by dou x of dou W by dou x into dx. Similarly, for Ny, it has dou W by dou y in the y direction, and due to a small increment in the other direction, it is given as dou W by dou y plus dou by dou y of dou W by dou y into dy. Similarly, for the shear forces Nxy, we have dou W by dou y plus dou by dou x of dou W by dou y into dx along the y direction, and along the x direction it is given as dou W by dou x plus dou by dou y of dou W by dou x into dy. Now, the strains on the middle surface of the plate caused by bending are neglected. Hence, the in-plane forces are solely due to the constant in-plane loads and do not vary with x or y. However, the lateral deflection W vary with x and y, giving rise to slopes and curvatures as indicated in the figure on the right hand side. Now, summation of the forces along x-axis sigma fx, we have sigma fx equal to minus nx into cos dou W by dou x into dy. Basically, we are resolving the components in the x direction. So, we have this theta, which is dou W by dou x. So, when we resolve it in the horizontal direction, it becomes nx into cos of dou W by dou x. Similarly, on the right hand side, it is nx into cos of dou W by dou x plus dou by dou x of dou W by dou x into dx. And similarly, for nxy, we have to use the same technique to get the equilibrium of the forces in the x direction. So, when we do so, we have sigma fx equal to minus nx into cos of dou W by dou x into dx. So, when we look at it, we have sigma fx equal to minus nx into cos of dou W by dou x into dy plus nx into cos of dou W by dou x plus dou by dou x of dou W by dou x into dx into dy plus nyx into cos of dou W by dou x plus dou by dou y of dou W by dou x into dy into dx minus nyx into cos of dou W by dou x into dx. Now, the summation of forces along y axis is given as sigma fy equal to 0. Here, sigma fy is also given with a set of equations similar to the one that we have described here. Here also, the horizontal component is given by the cos function. When we do the same summation, we get the equation as shown here. For small lateral deflections W, using small deflection theory, we have sin theta equal to theta and cos theta equal to 1. So, when we apply the simplification, we get the summation sigma fx is equal to 0. And when we do the same thing, we get sigma fy is equal to 0. Now, look at the sum of force components of nx forces along z axis, which is sigma fz equal to 0. So, when we do so, For the vertical component, instead of cos, it becomes sine. So, we have this components in the form of sine. Now, we have minus nx into sine dou w by dou x into dy. The minus sign is given because it is opposite to the positive z direction. So, we have minus nx into sine dou w by dou x into dy plus nx into sine of dou w by dou x plus dou by dou x of dou w by dou x into dx into dy. And the sum of force component ny forces along the z axis sigma fz is given as minus ny into sine of dou w by dou y into dx plus ny into sine of dou w by dou y plus dou by dou y of dou w by dou y into dy into dx. Now, the sum of force components nxy forces along the z axis is also given here. The same technique is used. When it is vertical, we use the sine components, and using the small lateral deflections w and using the small deflection theory sin theta equal to theta and cos theta equal to 1, we can further simplify these equations and we get the value of nx into dou square w by dou x square into dx into dy for summation of forces nx in the z direction, which becomes equation 1, and summation of forces in the z direction for ny, we get ny into dou square w by dou y square into dx into dy, which becomes equation 2. Similarly, when we sum the forces of nxy in the z direction, we have this equation here. We can simplify this further. Some terms gets cancelled out. When we do so, we have nxy into dou square w by dou x into dou y into dx dy plus nyx into dou square w by dou y into dou x into dy dx. When we add all the three components, which is the total sum of the forces in the z direction, we have nx into dou square w by dou x square plus ny into dou square w by dou y square plus nxy into dou square w by dou x dou y plus nyx into dou square w by dou x dou y into dx into dy equal to 0. Now, since the material of the plate is assumed to be isotropic, nxy is equal to nyx. So, this gives rise to the equation nx into dou square w by dou x square plus ny into dou square w by dou y square plus 2nxy into dou square w by dou x dou y into dx into dy is equal to 0, which becomes equation 4. So, these are the equilibrium equation of the in-plane forces. Now, the equilibrium of the shear forces is given in the picture here. Now, we have qx in the left hand side, and the right hand side we have qx plus dou qx by dou x into dx. Similarly, we have qy and qy plus dou qy by dou y into dy. So, the components of shear force in x and y direction are negligible. The sum of shear force components along the z direction is qx into dy, which is the shear force, plus qx plus dou qx by dou x into dx into dy minus qy into dx plus qy plus dou qy by dou y into dy into dx. So, which gives rise to the value dou qx by dou x plus dou qy by dou y into dx into dy, which becomes equation 5. So, now we have equilibrium equation of the in-plane forces. From 4 we have this equation, and then when we add the other equation 5, 4 plus 5 gives you a much bigger equation which includes the shear components. This becomes equation 6. Now, rewriting the shear force components in the form of moment m, we have the equilibrium of bending moments, as you can see here. Now, condition is the sum of the moments about the x-axis should be equal to 0. Note the terms at the start of the shear forces and moments are taken as positive, while the terms with partial derivatives are taken as negatives. Now, we have my into dx minus my into dou my by dou y into dy into dx minus mxy into dy plus mxy plus dou mxy by dou x into dx into dy minus qx into dy by 2, where the lever arm here is dy by 2 for qx plus dou qx by dou x into dx into dy by 2. Similarly, the lever arm is dy by 2 plus there is another qy, which is qy into dou qy by dou y into dy into dx, and whose lever arm is dy. So, multiply by dy is equal to 0. We can simplify this further. We can get the terms cancelled out, which is my and minus my. Similarly, mxy and minus mxy, and then qx into dy by 2, and then plus qx dy into dy by 2. So we get a big equation here. Now this dx into dy square can be neglected due to higher order terms. So we have this equation dou my by dou y minus dou mxy by dou x minus qy is equal to 0. Similarly, for moments about y axis, we have dou mx by dou x minus dou myx by dou y minus qx is equal to 0. Upon differentiating, we have dou qy by dou y equal to dou square my by dou y square minus dou square mxy by dou x dou y. The next term is dou qx by dou x equal to dou square mx by dou x square minus dou square myx by dou x dou y. Now we can substitute the above equations in equation 6. We have the terms dou qx by dou x and dou qy by dou y, which can be substituted. When we substitute here, we get another nice equation as shown here below, which becomes equation 7. Here we have 4 unknowns, which is mx, my, mxy and w. So we need 3 more relations in addition to equation 7. The additional relation will have to be obtained by considering the deformation of the plate, which is moment displacement relations. Now let's look at the moment displacement relation. Equations that express moment in terms of displacement will be obtained by relating moments to stresses, followed by stresses to strains, and from strains to displacement. Now let us look at moments to stresses. So we have this small element dx, dy and dz, and the middle surface is where the z starts. So the total thickness is divided as h by 2 at the top and h by 2 at the bottom. Now we take a small slice of plate and we call it as dz, which is at a distance z in the positive direction downwards, and we have the corresponding normal stresses sigma x and sigma y. Now the moments and stresses are positive in the direction considered. So we have mx equal to minus h by 2 to h by 2 sigma x into dz into z, and my equal to integral of minus h by 2 to h by 2 sigma y into dz into z, and mxy equal to minus integral of minus h by 2 to h by 2 tau xy into dz into z. The negative sign indicates that mxy is negative when z and tau xy are positive. To better understand this, it is important that you go and take a look at the slides that we have mentioned where the positive sign convention for the moments are given. You can quickly realize that mxy will be negative for the forces that are acting, that is shown in the figure here. So now we have the strain, which is epsilon x equal to 1 by E into sigma x minus mu into sigma y, and we also know that epsilon y equal to 1 by E into sigma y minus mu into sigma x. So which indicates that E into epsilon y equal to sigma y minus mu into sigma x, which indicates sigma y equal to E into epsilon y plus mu into sigma x. Now when we substitute that in the above equation, we have epsilon x equal to 1 by E into sigma x minus mu into E into epsilon y plus mu into sigma x. So when we take this further and simplify this, now we get an equation which is the normal stress sigma x relates the normal strain in the x direction as well as the normal strain in the y direction along with the Poisson's ratio and the Young's modulus. Similarly, we have sigma y equal to E by 1 minus mu square into epsilon y plus mu into epsilon x, and tau xy equal to E by 2 into 1 plus mu into gamma xy. These equations are equally valid for relating bending stress to bending strains or for relating total stresses due to in-plane forces as well as bending to the corresponding total strains. Now let us look at the xy plane to derive the strain displacement relation. To obtain a set of bending strain displacement relations, the xyz components of the bending displacement at a point in the plate is denoted by u sub b, v sub b and w respectively. Now we have a small element ABCD whose length is dx and width is dy, and it deforms to a dash, b dash, c dash and d dash. Now the displacement in the x direction is given as u sub b and in the y direction is given as v sub b, and the point b dash here is v sub b plus dou vb by dou x into dx, and similarly here we can see the point D moves downwards by v sub b plus dou v sub b by dou y into dy. Similarly, the point B moves in the x direction as u sub b plus dou ub by dou x into dx, and the point D dash moves by u sub b plus dou ub by dou y into dy in the x direction. Now we have u and v are the total displacements, and u0 and v0 are the in-plane forces which are constant, and u sub b and v sub b are due to bending, which is variable. So u can be represented as u equal to u0 plus u sub b and v equal to v0 plus v sub b. During bending of the plates, the thin lamina ABCD located at a distance z above the middle surface undergoes the displacement and the rotation. Here the strain epsilon x is given as change in length divided by the original length. The change in length is a dash b dash minus ab, and a dash b dash is given as dx minus ub plus ub plus dou ub by dou x into dx minus dx, which corresponds to ab, and divided by ab, which is dx. So when we do so, we get epsilon x equal to dou ub by dou x, and similarly epsilon y equal to dou vb by dou y. The shear strain is equal to the change in the angle dab, which is given as gamma xy equal to dou u sub b by dou y plus dou v sub b by dou x. Now let us look at the strain displacement relationship in the xz plane, which is given here. So we can see that the thickness of the plate direction is shown here. At the top it is z. Let's look at a point E at a distance z from the middle surface. During bending, the plane sections are assumed to remain plane. The displaced configuration is given here. It moves by a distance u sub b and by a distance w in the vertical direction. So the slope is given as dou w by dou x. The displacement u sub b of a point E located at a distance z above the middle surface is shown. So when we look at the small triangle here, we know that the horizontal distance is u sub b, the slanted distance is given by z, and the angle is given by dou w by dou x. And we know that ub here is defined as minus z into sine dou w by dou x when we resolve the components. The minus sign is because it is in the opposite direction, and so we have u sub b equal to minus z into dou w by dou x, simply because for small values of theta, sin theta equal to theta. Similarly, v sub b is given as minus z into dou w by dou y. The negative sign indicates that they are negative z and a positive slope corresponding to the positive displacement. We have epsilon x equal to dou ub by dou x and epsilon y equal to dou vb by dou y, and gamma xy equal to dou ub by dou y plus dou vb by dou x. So when we substitute the above terms based on u sub b equal to minus z into dou w by dou x and v sub b equal to minus z into dou w by dou y, we have epsilon x equal to minus z into dou square w by dou x square, and epsilon y equal to minus z into dou square w by dou y square, and gamma xy equal to minus 2z into dou square w by dou x dou y. Now we also know the relationship between sigma x and epsilon x. When we substitute the value of epsilon x into sigma x, okay, we get the strain displacement relationship here. Sigma x equal to minus Ez divided by 1 minus mu square into dou square w by dou x square plus mu into dou square w by dou y square. Sigma y equal to minus Ez divided by 1 minus mu square into dou square w by dou y square plus mu into dou square w by dou x square, and tau xy equal to minus Ez divided by 1 plus mu into dou square w by dou x dou y. We also know the moment displacement relationship given as mx equal to minus h by 2 to h by 2 into sigma x into z into dz. So when we substitute the value of sigma z here, we have minus h by 2 to h by 2 minus Ez divided by 1 minus mu square into dou square w by dou x square plus mu into dou square w by dou y square into z into dz. So we can take all the common terms outside, and we have minus h by 2 to h by 2 integral into z square into dz. So we get z cube by 3. When we substitute the upper limit and the lower limit, we get the value 2 into h cube by 24. This can be further simplified by making the term minus eh cube divided by 12 into 1 minus mu square. This eh cube by 12 into 1 minus mu square can be defined as flexural rigidity of the plate, as you can see at the down. So this equation now becomes mx equal to minus d into dou square w by dou x square plus mu into dou square w by dou y square. So similarly, the moment displacement relationship for my equal to minus h by 2 to h by 2 sigma y into z into dz, resulting in m sub y equal to minus d into dou square w by dou y square plus mu into dou square w by dou x square, and mxy equal to integral of minus h by 2 to h by 2 tau xy into z into dz, which gives rise to the value mxy equal to d into 1 minus mu into dou square w by dou x dou y. So from equation 7, we have a big equation in terms of mx, my and mxy. We can substitute that, and so in order to do so, we have to double differentiate mx, my and mxy. So we have dou mx by dou x equal to minus d into dou cube w by dou x cube plus mu into dou cube w by dou x dou y square. So dou square mx by dou x square equal to minus d into dou power 4 w by dou x power 4 plus mu into dou power 4 w by dou x square dou y square. Similarly, we do the same thing for dou my by dou y. So it gives rise to the value dou square my by dou y square equal to minus d into dou power 4 w by dou y power 4 plus mu into dou power 4 w by dou x square dou y square. Similarly, for mxy, we get dou square mxy by dou x dou y equal to d into 1 minus mu into dou power 4 w by dou x square dou y square. Now we can substitute all the above in the equation 7, and we can simplify this further. And we also know that the flexural rigidity of the plate is Et cube or Eh cube divided by 12 into 1 minus mu square, where h is the thickness of the plate. And we get some terms that are getting cancelled here, and we get an equation here. And the equation here can be further simplified by taking the flexural rigidity d outside the plate and all the displacement component on one side and all the force component on the other side. And this equation is known as von Karman's equation. This is the differential equation of the plate buckling under the action of in-plane forces Nx, Ny, Nxy. But for uni-axial compression, we can set Ny and Nxy is equal to 0. So we get a further simplified equation, which is d into dou power 4 w by dou x power 4 plus 2 into dou power 4 w by dou x square dou y square plus dou power 4 w by dou y power 4 is equal to nx into dou square w by dou x square. This is the fourth order differential equation for a plate, using which we can obtain the critical buckling stress for a plate. Now let us solve a problem for a plate subjected to uni-axial compression. Consider a simply supported rectangular plate subjected to uni-axial compression here. Nx is the force that is applied in the x direction. The plate is having a length A and a width B, and all the four sides are simply supported, as you can see here. A schematic of the deformed shape is also shown on the right hand side, where you can see that the strip AB corresponds to the length of the plate and the strip CD corresponds to the buckled shape across the width of the plate. The assumptions are the edges of the plate are free to move in the plane of the plate. No in-plane forces in addition to the applied load Nx can therefore develop as the plate is uniformly compressed. Hence, Ny is equal to Nxy is equal to 0. Now, the differential equation for the plate is given as d into dou power 4 w by dou x power 4 plus 2 into dou power 4 w by dou x square dou y square plus dou power 4 w by dou y power 4 is equal to nx into dou square w by dou x square plus ny into dou square w by dou y square plus 2 nxy into dou square w by dou x dou y. This is the differential equation of the plate under the action of in-plane forces nx, ny and nxy. By setting ny equal to nxy equal to 0, this equation reduces to d into dou power 4 w by dou x power 4 plus 2 into dou power 4 w by dou x square dou y square plus dou power 4 w by dou y power 4 equal to nx into dou square w by dou x square. Since nx is compressive nature, it is negative, so we can take it to the other side and it becomes d into dou power 4 w by dou x power 4 plus 2 into dou power 4 w by dou x square dou y square plus dou power 4 w by dou y power 4 plus nx into dou square w by dou x square equal to 0. Now all the four sides are simply supported, so the lateral deflection and the bending moment at the ends is equal to 0. Now at x equal to 0 comma a, the lateral deflection is 0, which is w equal to 0, and at y equal to 0 comma b, the lateral deflection again is 0. And mx is given as minus d into dou square w by dou x square plus mu into dou square w by dou y square, which is also equal to 0. Similarly, my equal to minus d into dou square w by dou y square plus mu into dou square w by dou x square is equal to 0. Since the lateral deflection w is 0 along each of the boundaries, dou square w by dou y square, which is the curvature, is equal to 0 at x equal to 0 comma a. You can see that the dou square w by dou y square can be cancelled and equated to 0. Similarly, the dou square w by dou x square is equal to 0 at y equal to 0 comma b, which means that in the term my, the dou square w by dou x square term also gets cancelled. However, here d cannot be 0 because d is the flexural rigidity of the plate, which is a combination of the material properties as well as the geometric properties. Hence, for mx equal to 0, dou square w by dou y square should be equal to 0. And similarly, for my equal to 0, dou square w by dou y square should be equal to 0. These are the boundary conditions of the plate here. W equal to dou square W by dou x square equal to 0 and W equal to dou square W by dou y square equal to 0. Now the general solution for a partial differential equation is very difficult to obtain. So let us assume the solution to be in a series form where W equal to sigma m equal to 1 2 3 and sigma n equal to 1 2 3 a sub mn into sin m pi x by a into sin n pi y by b. Here m is the number of half sine waves in the direction of loading, which is in the x direction, and n is the number of half sine waves in the direction perpendicular to the loading, which is in the y direction. Let us check if the solution satisfies the boundary conditions. At x equal to 0 comma a, W equal to dou square W by dou x square equal to 0. So we have W equal to a mn into sin m pi into 0 divided by a into sin n pi y by b, which is equal to 0. Similarly, at x equal to a, W equal to a mn into sin m pi a by a, which gives rise to the value sin m pi. So again this term is also 0. And for dou square W by dou x square, we have minus a mn into m pi by a the whole square into sin m pi x by a into sin n pi y by b. So here when we substitute x equal to 0, we have this entire term becomes 0 because sin 0 is 0. Similarly, at x equal to a, we get the term sin into m pi a by a, which again also becomes 0. The second boundary condition is at y equal to 0 comma b, W equal to dou square W by dou y square equal to 0. So when we substitute the value y equal to 0, we have W equal to 0. Similarly, when we substitute the value y equal to b, the W term again becomes 0 because sin pi is 0. And for dou square W by dou y square, we have minus a mn into n pi by b the whole square into sin m pi x by a into sin n pi y by b. When we substitute y equal to 0, again the term becomes 0. And similarly, when we substitute y equal to b, again the term becomes 0. So both the boundary conditions are satisfied, and from Von Karman's plate buckling equation, we have the above term d into dou power 4 w by dou x power 4 plus 2 into dou power 4 w by dou x square dou y square plus dou power 4 w by dou y power 4 plus nx into dou square w by dou x square equal to 0. So let us find the partial differentials in this equation. Here dou w by dou x is equal to a mn into m pi by a into cos m pi x by a into sin n pi y by b. So when we differentiate it twice, we get cos as minus sin. So we have minus a mn into m pi by a the whole square into sin m pi x by a into sin n pi y by b. And dou cube w by dou x cube is minus a mn into m pi by a the whole cube into cos m pi x by a into sin n pi y by b. When we differentiate it the fourth time, we have dou power 4 w by dou x power 4 equal to a mn into m pi by a the whole power 4 into sin m pi x by a into sin n pi y by b. So we have now dou square w by dou x square into dou y is given as minus a mn into m pi by a the whole square into n pi by b into sin m pi x by a into cos n pi by b. When we differentiate it again, we have dou square w by dou x square dou y square equal to a mn into m n pi square by a b the whole square into sin m pi x by a into sin n pi y by b. Now partially differentiating with respect to y, we have dou w by dou y equal to a mn into n pi by b into sin m pi x by a into cos n pi y by b. Dou square w by dou y square equal to minus a mn into n pi by b the whole square into sin m pi x by a into sin n pi y by b. Dou cube w by dou y cube equal to minus a mn into n pi by b the whole cube into sin m pi x by a into cos n pi y by b. So the fourth order differentiation, which is dou power 4 w by dou y power 4 is equal to a mn into n pi by b the whole power 4 into sin m pi x by a into sin n pi y by b. Now substituting all the derivatives in the partial differential equation, we can get a big differential equation as you can see here on the screen. And you can take the summation sigma m equal to 1 2 3 and sigma n equal to 1 2 3 a mn into the bracket open m pi by a the whole power 4 plus 2 into mn pi square by ab the whole square plus n pi by b the whole power 4 minus nx by d into m pi by a the whole square sin m pi x by a into sin n pi y by b equal to 0. Now the only way this infinite sum is equal to 0 is when the coefficient is 0, as you can see, that is boxed in the red color. Now even here we can see that the AMN value cannot be 0, because if it is 0, then nx can have any values, which is a trivial solution. So the one that is inside the square bracket has to be 0. So when we equate that to 0, we can simplify this further as pi power 4 into m square by a square plus n square by b square the whole square minus nx by d into m pi by a the whole square equal to 0. This is because we know that a square plus 2ab plus b square equal to a plus b the whole square. So we are using that identity here. Here a equal to m pi by a the whole square and b equal to n pi b the whole square. So here we get nx equal to d into a square pi square by m square into m square by a square plus n square by b square the whole square. Or we can also write this as nx equal to d a square into pi square divided by m square into m by ab the whole square into mb by a plus n square a by mb the whole square. Now this gives rise to the equation nx equal to d into pi square by b square into mb by a plus n square a by mb the whole square. This nx depends on the dimensions, physical properties and number of half sine waves the plate buckles into. So n increases with the increase in n. So the minimum value of nx can be obtained by setting n equal to 1, which is the minimum value, which means that the number of half sine waves in the direction of y is limited to 1. So the plate buckles in a single half sine wave in the y direction. So now this gives rise to the equation nx equal to d pi square by b square into mb by a plus a by mb the whole square. The number of half sine waves in the x direction that correspond to a minimum value of nx is found by minimizing nx with respect to m. Now taking p equal to a by b, nx equal to pi square d by b square into m by p plus p by m the whole square. So when we take the differentiation with respect to m, we have pi square d by b square into d by dm of m square by pi square plus p square by m square plus 2 equal to 0. So when we differentiate that, m square becomes 2m and 1 by m square becomes minus 2 by m cube. So when we get this, we have pi square d by b square into 2m by p square minus 2p square by m cube equal to 0. Now we can take the 2 outside and we know that pi square d by b square into 2 is not equal to 0. Hence m by p square minus p square by m cube should be equal to 0, which means that m equal to p. So m equal to p is nothing but m equal to a by b. Now substituting m equal to a by b in the equation nx equal to pi square d by b square into mb by a plus a by mb the whole square. Here since n equal to 1, we get a simplified equation. So here nx equal to pi square d by b square into a by b into b divided by a plus a by b into b the whole square. So this gives rise to the equation pi square d by b square into 2 square. So nx equal to 4 pi square d by b square. So this becomes the critical value, which is nx critical equal to 4 pi square d by b square. Now in generic terms, we can write nx equal to k into pi square d by b square, or k can be defined as mb by a plus n square a by mb the whole square. K is defined as the factor which is based on the ratio of a by b and on the number of half sine waves m and n. And the minimum value of nx was obtained by setting n equal to 1. And the number of half sine waves in the x direction m is nothing but the ratio a by b. And when we plot k versus a by b, which is the k is the elastic buckling coefficient and a by b as the aspect ratio of the plane, we get what is known as Garland curves. So we can see a series of curves which are Garland in nature. So m equal to 1, we have a blue color curve, m equal to 2, we have an orange color curve, and m equal to 3, it becomes flatter, and we have a gray color curve, and at m equal to 4, we kind of slightly have an yellow color curve. You can see that. Right? It is evident from these curves that there exists an unlimited number of values of k corresponding to any given a by b that satisfy the equation of k. The solid line obtained by connecting the lower branches of the various curves gives the critical value of k as a function of the aspect ratio a by b. In addition, the solid line indicates the number of half sine waves into which the plate buckles corresponding to a given a by b. For example, the buckling stress coefficient k is obtained from the curve for m equal to 1 for all plates with a by b less than root 2. These plates therefore buckle into a single half sine wave in the x direction. For plates with a by b between root 2 and root 6, k is taken from the curve for m equal to 2, and these plates accordingly buckle into two half sine waves in the longitudinal direction, as you can see from the picture above. As long as a by b is relatively small, k varies considerably with the aspect ratio, which means that there is a huge variation in k when the aspect ratio is very low. As you can see, for m equal to 1, the curve is very steep and it comes from k equal to 6 and goes down to k equal to 4, and then it jumps up to k equal to 5, something like that. So you can see that as long as the A by B is relatively small, K varies considerably with the aspect ratio, and a curve like the one in the above figure is required to obtain the correct value of K. However, for A by B greater than 4, which is the aspect ratio greater than 4, indicating that it is slightly becoming a long plate, the variation of K from 4.0 is almost negligible, and K equal to 4.0 is therefore a satisfactory approximation for plates with A by B greater than 4. So, in essence, the value of K depends on the aspect ratio of the plate A by B. It also depends on the boundary condition of the plate and the applied loading condition. Let us substitute D and rewrite Nx in terms of sigma x, which indicates Nx equal to sigma x into T. So, we have sigma x equal to K into Et cube divided by 12 into 1 minus nu square into pi square by B square into 1 by T. So, when we rearrange the terms, we have sigma x equal to K into Et square divided by 12 into 1 minus nu square into pi square by B square. This can be rewritten as sigma x equal to K into pi square E divided by 12 into 1 minus mu square into B by T the whole square, where K is the elastic buckling coefficient, E is the Young's modulus of the plate, mu is the Poisson's ratio, and B by T is the slenderness of the plate. Now, for plates, sigma x equal to K into pi square E divided by 12 into 1 minus mu square into B by T the whole square. And here, as we discussed before, K is the plate buckling coefficient or elastic plate buckling coefficient. And for columns, sigma critical is defined as C into pi square E divided by L by R the whole square. Here, L by R is the slenderness ratio of the column, and C is defined as 1 by K square, and K is the effective length factor. The comparison of the equations indicates that the critical stress of both the plate and the column are directly proportional to the stiffness of the material E and inversely proportional to the square of the slenderness ratios. For a plate, the slenderness ratio is defined as B by T, and for a column, the slenderness ratio is defined as L by R. The critical stress of a column thus depends on its length L, whereas that of the plate depends on the width of the plate B, and it is independent of the length. Now, let us look at the approximations for the out of plane displacement W for different boundary conditions. For fixed and fixed condition, W is given as A into 1 minus cos 2 pi x by A into 1 minus cos 2 pi y by B. For simply supported fixed, W is given as A into sin pi x by A into 1 minus cos 2 pi y by B. For simply supported free, it is given as W equal to A into sin pi x by A into y by B. It should be noted that these boundary conditions represent the boundary conditions for the unloaded edges of the plate. The loaded edges of the plate are almost always assumed to be simply supported. We will see more of these cases in the next classes. Thank you very much.